So, good morning. Welcome to Krishna's classroom. We begin with a new series of lectures on metric spaces. And you might wonder why this urgency. This is specifically done for the students at the Amrita University at the Amritapuri campus who is undergoing a course of the 5th semester MSc program, integrated MSc program, entitled Real Analysis 2. The course code is 18 Mat 305. This is totally irrelevant for the general audience, and the title of the paper is Real Analysis 2. For various reasons, I thought that is better to put it on my channel so that even future generation would benefit from this effort. I have given live lectures to the students there and covered probably 1/3 of the syllabus, and I have no intention to repeat the whole thing in detail, but probably it would be better still to recall some of the concepts and or just give a hint to what all things we have already looked at, and that would be just connect everything. In this lecture, want to explore continuity of functions, or the concept of continuity of functions defined from one metric space into another. But before that, let me just say what a metric space is. Metric space is essentially it's a non-empty set with a function d defined from R satisfying certain properties, namely that d of xy is greater than or equal to 0, d of xy equal to 0 if and only if x equal to y. That is the first set of conditions that we impose. The second set of conditions is that it is symmetric in the sense that dxy equal to dyx. Then third condition is that it satisfies the triangular inequality, namely dxy is less than or equal to dxz plus d. This is for x, y, z belonging to x. Now this defines a metric. This, if you just connect with what you are already familiar with, it is that on R, the usual metric D is defined as mod x minus a. And you can check that all these properties are satisfied. So this is an example. In fact, everything has come out of the experience of working on R. Generalize this. But there could be some very curious types of metrics that come, and usually when you want to formulate a problem mathematically, then you choose the right kind of metric that suits the problem. That's the general technique. Now, you have the other extreme side of it, namely the so-called discrete metric. So let me just write discrete metric on, so x non-empty, then d x y is defined as 1 whenever x not equal to y and equal to 0 equal to. Now you can verify that this is a metric. So this is the first example, second example. Now there are several metrics that you can have. So for instance, if this needs some work, of course, if x is a non-empty set and D is a metric, on x, then D tilde defined as for every xy is a metric on. Now, what is significant is that it's a bounded metric. So you see that D tilde so it's a bounded metric. Whereas the metric that you are already familiar with on R is not necessarily bounded. Then of course I just don't want to spend time on these things, namely you can define C can be made a metric space and D defined as small z1 minus z2. This is a metric. So this is a metric space that you can verify. Then you have on Rn D1, so D1 x y defined as maximum of so that's how say metric, right? And there are other metrics of interest that we impose on this. I'll spend something like half an hour on this kind of little things, which I think you should take some pains to verify all this. It's all discussed in detail in any book on metric spaces. Especially one beautiful book that you can look into is the one written by Kumar, and you know he's a very reputed mathematician and teacher, and his books are very enchanting, and he looks at problems geometrically, and that's something very important, or something that distinguishes him from others. It's very fascinating to get an insight into the concepts. His expositions are often excellent. So there's a book written by him, namely Topology of Metric Spaces. Yes, Kumaration. Metric spaces. And my lectures are broadly based on this book. And apart from that, our most trusted econ analysis, namely R ruling, principles of mathematical analysis. And there are scores of books written on this particular topic. So you can take any one of them, look at it. So I would refer you to these two books. Yeah, what I have been trying to do was this. On Rn, now this is the fourth example. So fifth example, on Rn D2, this is the usual metric, where D2 defined as this one is, the notation is D infinity. Sorry. Yeah, this is xi minus yi square half 1 to n. This is the usual distance notion. R. That's what's called the Euclidean metric. Then you have this, I should have put in the beginning. Is a metric. And then you can have, take any non-linear space, symmetric space. Now I can just say what normally linear space is briefly, and then set out the induced metric. See, many of these statements do need a elaborate proof. Okay, so there are two things as you see here. X a linear space over R of C now we define, I am not going into the details of this. You, all those who have done linear algebra would recall what a linear space is. Now you define, and of course when x and y are in X, then x plus y is in X, a scalar multiple of x is in capital X, and so on, and which satisfies, this is the rule of addition and scalar multiplication that you define, which is modeled on R3 or R2. Okay, the vectors in R2 or R3. So these are called vector spaces or linear spaces. Now let me define what the norm is. Norm is a function. We denote this by this. Is a map from X to R such that norm of X is greater than or equal to 0 denominator X, norm of X equal to 0 if and only if X equal to 0. The norm of alpha X rather I should put it this way, maybe this is not the right order, this way. Norm of X plus Y is less than or equal to Y and third one, norm of alpha X equal to mod alpha into norm of X. For every R or C. Yeah. This defines what you call a norm or a concept of length on the vector space X. Now there are examples, exotic examples, where norms are defined in all different ways, and you can see the details in the various books. Now, the metric that is induced by the norm is this dxy now you can prove that all the conditions of the normed linear space are satisfied. So all normed linear spaces are metric spaces with the induced metric. Okay. Now another special normed linear space that we would be probably interested in will be the following. This is what are called inner product spaces. This is the generalization of the concept of dot product. on Rn. Okay, so we will next introduce what are called inner projections. We have X, a linear space. See, now we define an inner product as follows. An inner product dot product generalized is a map X cross X R with the property that so you are working in a linear space. So that's the first property. Second property is X plus Y for every X, Y, Z, X. Third property is alpha X, Y equal to alpha times XY, and you also have the property that or rather the third property I put the following, something analogous to symmetry. Now that is X, Y equal to Y, X conjugate. Now conjugate is relevant when you work with C. Okay. So this is essentially C. It's a matter. Okay. Now the fourth property is that alpha X C. And a fifth property, that is phi, which is X alpha Y equal to alpha conjugate XY. This is a consequence of 3 and 4. So this defines it, and this is what. Now if you define, now you can prove that every inner product space is a normally linear space. The converse is not true. The converse is not. Then what you have is this. Therefore, every inner product space is a. And how do you define this norm? The norm X is defined by X. You know that XX is always real, because if you apply this, see, inner product of X with Y, inner product of X with X is equal to inner product of X with X conjugate, therefore it is real. And you know that this is greater than or equal to 0, therefore you can take the square root of that, the positive square root of that. The positive square root is defines what is called the norm of X, and this is the Euclidean norm in that space, subordinate to the inner product that you introduce. Correct. Now what you have, so every inner product space is a because you know that every inner product space is a normally linear space, and every normally linear space is a space. Okay, so that much is there. Now let me not go into, there are a lot of finer details that you should be looking at, and I would refer you to the books I have mentioned, or to any other book on these topics. Now we start working on the topology of the space. Again, the inspiration comes from what we know of the real line. So recall, so you have R, D is a U-field. It is dxy mod x minus y for every x and y. Now, on the real line, choose an x naught. So you mark out the interval for epsilon positive. This consists of all those x belonging to R such that mod x minus x, or dx x naught is less than epsilon, where epsilon is positive. So this is what you call the epsilon neighborhood of now this interval is called we use this word open without really the open neighborhood of x naught of radius r, sorry, epsilon. Now let us write down analogously. So take any arbitrary metric space with a metric. So in XB, define B x naught epsilon to be the set of all x belonging to x such that d of x now this here it is actually mod x minus x naught. So it has been recast in the language of D for the real line, and this is now for any general space we do this. Now this is what is called an epsilon neighborhood of x naught. So for instance in R2 the usual metric, suppose this is the point x naught, is going to be the interior of the ball of radius epsilon, and the shape of this is a circle in the usual metric. But if you were to use other different metric, then you are going to get sets of different shape. So this is what is called B x naught. Okay, but only the interior is there, so that the boundary is not included. So let's just cut the boundary. But we will also use the notation which we shall need. This is called the closed neighborhood of x naught. This you define as the notation that we shall later use. At that time we can use it without any such that The difference is that here it is strictly less than epsilon, here it is less than or equal to epsilon. So it is actually the closed ball that you get. Okay. So later you can show that this is a so-called open set, this is a closed set. Okay. So this is what you call the open neighborhood. This is called epsilon neighborhood. So this is called an open although we have not yet said anything about this word open, but soon we will make it clear. Now we define what are called open sets and closed sets. Suppose A is a subset of X. Okay. A is said to be open if every point open neighborhood lying entirely what does it mean? That is X belonging to A implies there exists an epsilon positive such that B now this epsilon may depend on strictly speaking on the position of X, how close it is to the so-called boundary. Okay. Right. Now what one can prove is that one of the results that you can prove is that having defined an open set, what you can prove is the following. We'll say something about the process. I am not going into examples. There are plenty of examples that you take. For instance, geometrically, this is what it is. Suppose you take R2, for instance. Suppose this is a set whose boundary is not there in the set, then you choose, given an X, you choose an epsilon, you take the distance from X to the boundary and something less than that, and that we have not defined actually. It is the, see, you take dxy where yeah, or maybe write it more clear. Okay, let me just hint the proof of this here. So consider okay. Then Bxr such that okay, it means okay. Let me work with the R2. Okay, this is Bxr, right? Now what you do is, suppose you choose an arbitrary element y belonging to this. What you do is choose, look at the radius. Now what one does is choose, so dxy, suppose y belongs to, so dxy greater than or equal to 0. So you choose a delta which is less than or equal to r minus. Now you can show that by delta is containing, so you will have to use the properties of the matrix to prove this. So that is very interesting to have it. So I am not going to do this. So essentially what you are looking for is something. So that is the geometry of the problem. I just wanted to show the geometry of them. That's all. Okay. Right. So, but going to all other details. So, every open set is a subset A of a metric space is said to be open if for each point in the set there exists an open neighborhood contained entirely in the set A. That's what we have defined as open set. Now we say that a set B is closed if A complement or B complement open. For instance, you have take positive. Then you see that take a complement of that. So this is it, x. So you have the boundary also in it. This set. Now you see that take a point outside, then you can find a neighborhood lying inside that. Therefore, this is what's called a closed set. Or on your simple analogy on the real line, suppose you have an interval AB. Suppose you consider the interval AB then AB is open. AB with A and B included is closed since AB complement is equal to minus infinity to A union B dt. Now both are open sets. Okay. Now one of the results which is very significant is that suppose some index set where I is some index set, not necessarily countable or finite or any such thing. I an index set then Further, if A1, AN are open sets, in X, then intersection AI, I running from 1 to n, open. But you cannot say that countable intersection of open sets is open. So any finite intersection of open sets is open. That is, finite intersection of here, of course, this means that arbitrary union of open sets is open. Open, finite intersection of is open, and then you have X is open, and the empty set phi is open. So any collection, let subsets of X satisfying the properties mentioned above. Okay. Such that tau is closed under arbitrary union and closed under finite intersection. Further, X belongs to tau and then tau a collection of open sets which constitute the topology. Now this is the definition of the topology. So X with tau is called a topological space. Topological space. Now all open sets, now see all metric spaces but the converse in general does not hold. That is something about the topology. So I think I should make some remarks on this. You see that our model was the real line with the length concept. Then you have got what are called the open intervals. We can, for each point, you can introduce the concept of what are called open neighborhoods. And you see that we defined what is called an open interval, or every open subset of R has the property that each point in it has a neighborhood, open neighborhood, completely contained in the space. Okay, so this is where we started with. We generalized it immediately to what are called metric spaces. Because once you have the metric, see, you are endowed with the facility to talk about distances as you have on R. So using that, we defined what are called the open sets. And then we proved that the open sets have the following properties. That the open sets are closed under arbitrary union and finite intersection. X is an open set and empty set is trivially an open set. Okay, so open sets in the context of a metric have these set of properties, and this provides the space with the necessary topology. But then we jump from the one step further, because we take this as the starting point. Okay, instead of considering this, what we do is we take an X, a non-empty set, and then you have the set of all subsets of X, and you take a sub collection of subsets which have the property that they are closed under arbitrary union and finite intersection, and X is in this collection and the empty set is also in this collection. Then X along with this particular tau is going to be very similar to what we have done here. Okay, so we shall call these sets as open sets, and the whole collection is set to provide what is called a topology for the for the space, or X now along with this collection of so-called open sets becomes a topological space. Okay, so I think we have discussed it in the class elaborately and put a lot of remarks about it and gone into the details. So I don't want to digress beyond that. Now, you see that it's very simple to show that this arbitrary intersection of open sets need not be open. So, arbitrary intersection of for example, you take R. Now consider these open sets. This is an arbitrary collection of open sets. Each but the intersection AN equal to the singleton 0. This is not that is why we talk about what are called the finite intersection of sets. Now, this is somewhat the preliminaries of what some of the preliminaries that we have to do. We have to look at for in the context of what are called metric spaces. Now we are going to do analysis of this. Now we can once again talk about what are called it's called a convergence, concept of convergence. So we revisit R. Is equal to R. On that, we define, okay, let be a sequence No, I am not going into the definition of the sequence because it's a map from the set of natural numbers to R, give you a sequence of elements. So it's actually X mapped from this is a real sequence. So Xn, the value of X at n, this we designate as Xn. That's a traditional notation. Should have been strictly limits. So that would have made this the definition more transparent. Okay, so that's a sequence. Now, you recall that we say that Xn converges to modulus of as n tends to infinity. Or we can put it this way, and this we designate by saying that xn converges to x. Okay. Now, so this is in the, so if you take R with the usual D, then this statement is D is to 0 as tends to infinity. Then we say that xn converges to x. This is a recasting of the whole concept in terms of D. Therefore, now what you can do? So we say that you can talk about X, a non-empty set, XD be a metric space. Then suppose Xn is a sequence in X. We say that Xn converges to X, D Xn X goes to 0 as infinity. Now these are real numbers. So you can, what do we mean by this goes to 0, etc. So that's no problem at all. That's about the convergence. Okay. And what does this mean? This can be once again reformulated. We reformulate it as follows. We reformulate it as follows. So what we have is this. We have xd d, then you have the sequence contained in x. We say that if given epsilon, there exists a n depending on epsilon such that d see, this is what happens. On the real line, you have x, then you are talking about a sequence going to this. What you are talking about is, you are looking at, see, dxn x less than epsilon is essentially mod xn minus x less than epsilon. What is that? That is same as xn x minus epsilon to x plus epsilon. I said this is an open net. So this is x minus epsilon. So the statement that xn converges to x means for every choice of epsilon positive, there exists a neighborhood x minus epsilon to x plus epsilon of x such that xn belongs to or the distance or xn belongs to this open interval for every n greater than n epsilon. So if epsilon becomes smaller, this number will increase. But nevertheless, what is happening is that every xn would be inside this neighborhood from some stage onwards. Then you say central x. Okay. So this will be the formulation of convergence in terms of T. I mean, this is another way of stating this. Okay. And more generally, now you can use this idea to introduce what is called continuity. So I think I'll stop here in this lecture. Maybe I'll take it up in my next lecture. This is of course preliminaries. I think I probably changed the title here. Expenses, right? Preliminaries. Okay, so that is the first lecture. So let me now, after this, we will straight away go into define what is called continuity of functions or mappings between two non-linear spaces. So our theme for the next lecture will essentially to consider continuous functions. Thank you very much. And that gives the preliminary talk. And from now on, we will be going into depth of these things. But these preliminaries one should look into and be familiar with, and should do a detailed work on that. I have already introduced in the classroom, and those who have already seen it, there should be no problem in starting from the next lecture. Thank you very much. See, this particular series of lectures is although directed towards the students at the Amrita University, at Amritapuri, who are undergoing the course on Real Analysis 2, the course entitled Real Analysis 2 in the 5th semester. However, anybody who is interested to learn these things or doing similar things at different places is welcome to look at it. Thank you very much.